Hello, my friends, and welcome to Hafee Sleep. Whether you're tuning in from a bustling city just winding down, a quiet town deep in the night, or somewhere halfway across the globe where the sun is still high, we're so glad you're here. Tonight, we're going on a journey unlike any other. A journey across space and time to the very heart of our home in the cosmos, the Milky Way galaxy. So find your coziest spot, settle in, and let your imagination drift among the stars. If this sounds like the kind of escape you love, don't forget to subscribe to Hafee Sleep and hit that like button. It truly helps our little channel grow. And we'd love to know, where in the world are you watching from, and what time is it for you? Drop a comment below and share your moment with us. Now, close your eyes, take a deep breath, and let's begin. Imagine, for a moment, that you are standing on a quiet hilltop on a perfectly clear, moonless night. Far from the glare of city lights, you look up. And there, arching across the heavens like a ghostly river of spilled diamonds, is a sight that has captivated every human civilization since the dawn of our species. The Milky Way. It is a breathtaking, almost mystical spectacle. But what you are truly seeing with your own eyes is the collective glow of hundreds of billions of stars, the very structure of our home galaxy, seen from within. You are not just looking at a beautiful sight. You're looking at your own city, your own neighborhood, on a scale so immense it defies everyday comprehension. This, right here, is our galactic address. And for this journey, you don't need a telescope or a spaceship. All you need is your curiosity. So, get comfortable, and let's embark on an epic voyage of exploration. Let's unravel the story of our Milky Way. Our story begins not in a specific place, but in a specific time. A time before the Earth, before the Sun, before even the Milky Way itself existed. We have to rewind the cosmic clock back over 13 billion years to a point just a few 100 million years after the Big Bang itself. So let's settle in and really picture this moment, this cosmic dawn. Imagine the universe as a vast, dark, and incredibly simple soup. The main ingredients? Just two: hydrogen and helium. That's it. After the colossal fireball of the Big Bang had expanded and cooled for a few 100 million years, this was what was left. A thin, foggy broth of these two simplest gases, stretching out in every direction for distances so immense they are almost impossible to fathom. There were no landmarks, no stars to navigate by, no light at all, in fact, except for the faint, fading afterglow of the birth of the universe itself, which by this time had cooled to a uniform, invisible microwave whisper. It was a profoundly dark and quiet place, but it was not perfectly uniform. This is the most crucial part of the whole story. You see, that primordial soup had tiny, tiny ripples in it. Imagine the surface of a perfectly still pond, and then a single tiny raindrop falls, creating the faintest of ripples that spread out. Now imagine those ripples are frozen into the fabric of space itself. These imperfections, these slight variations in density, some patches were just a tiny, tiny bit thicker than others, were the seeds of everything to come. They were the cosmic blueprints, imprinted by the wild physics of the Big Bang. Without these tiny fluctuations, gravity would have had nothing to grab onto. The universe would have remained a forever expanding, perfectly smooth and utterly boring sea of gas. There would be no us, no stars, no galaxies, no story to tell. So these tiny ripples are the reason we are here today, talking about this. It's a humbling thought.
Now, enter the main character of our story, gravity. Gravity is the ultimate slow and steady winner. It is the most patient force in the universe. It doesn't need to be flashy. It just is. And it never, ever stops working. Its rule is simple. Anything that has mass attracts any other thing that has mass. The more mass you have, and the closer you are, the stronger the pull. So gravity looked out across this vast, rippled sea of gas and saw opportunity. Those slightly denser patches, those cosmic overdensities, had just a little bit more gravity than the less dense areas around them. So, ever so slowly, over millions of years, gravity began to pull the gas from the thinner areas toward the thicker areas. It was a cosmic gathering, a gentle pulling together of material. Think of it like this. If you have a stretchy sheet and you place a single heavy marble in the center, it will create a dip. If you then scatter tiny ball bearings across the sheet, they will all naturally roll inward toward the marble. In our early universe, the slightly denser patches of gas were like that marble, creating a tiny gravitational dip in the fabric of space-time itself. The surrounding gas was like the ball bearings, slowly, inevitably, drifting inward. As more and more gas gathered into these pockets, they became even denser, which made their gravitational pull even stronger, which attracted even more gas. This is what scientists call a runaway process, a positive feedback loop. The growth started imperceptibly slow, but it began to snowball over time. These gathering clouds of gas were unimaginably huge. We're talking about clouds that could be hundreds of thousands of light years across. To put that in perspective, a single light year is about 6 trillion miles. So these were behemoths on a scale that truly defies human comprehension. They were the primordial raw material, the cosmic lumber yards, from which entire galaxies would eventually be built. And as these vast clouds collapsed under their own immense weight, something interesting started to happen. They didn't just collapse into one single giant object. They became unstable. The cloud would start to ripple and churn from within. And much like a mist condensing into individual droplets of water, these giant gas clouds would fragment and break apart into smaller, dense clumps. Each of these smaller, collapsing clumps was destined for a spectacular future. Each one was a star in the making, a protostar. And because these clouds were so enormous, they gave birth to thousands, even millions, of these protostars all at once, creating the first ever star clusters in the universe. Now here's where things get really interesting. This first generation of stars, often called population 3 stars by astronomers, a bit of a boring name for such fascinating objects, were nothing like the stars we see in our night sky today. They were the true titans, the leviathans of the cosmos. They had a pure diet of only hydrogen and helium. There were no heavier elements available to them yet, and they formed from these massive, pristine clouds. Without metals, which is what astronomers call any element heavier than helium, to help cool the gas and allow it to fragment more easily. The clumps that formed had to be much, much bigger to begin the process of collapse. So these first stars were monsters. They weren't just a little bigger than our sun. They were colossal. Many of them were between 100 and 1,000 times more massive than our sun. Can you imagine a star that size? Our sun is already so huge that over 1 million Earths could fit inside it. These stars were on another level entirely. And with immense size comes immense gravity. The gravity at the core of one of these behemoths was absolutely crushing. This created unimaginable pressure and heat. The core temperatures of these stars would have been scorching, many times hotter than the core of our sun. This extreme environment meant that these stars lived their lives at a breakneck pace. A star like our sun, is a model of efficiency and longevity. It has been burning steadily for 4.6 billion years and has about 5 billion more to go. It's a long-distance runner. These first massive stars were the ultimate sprinters. They burned through their vast reserves of hydrogen fuel in a frantic race that lasted only a few million years. In cosmic terms, that's not even a blink of an eye. It's a fleeting instant. They shone with a fierce, intense blue-white light that would have been terrifying and beautiful to behold. But this furious burning couldn't last. When such a massive star runs out of hydrogen fuel in its core, the balance of its life is over. The outward pressure from nuclear fusion that had been holding up the star against the immense inward pull of gravity suddenly drops. And gravity, always waiting, always patient, wins in an instant. The core collapses catastrophically. In a matter of seconds, the star's inner core, which might be several times the mass of our entire sun, is crushed into a sphere only a few dozen miles across. The shock wave from this sudden violent collapse ripples outward through the entire star, and the outer layers rebound off the incredibly dense core and are blasted out into space in one of the most energetic events in the entire universe, a supernova explosion. The death of these first stars was not an end. It was a magnificent, violent, and creative beginning. The ferocious energy of a supernova is so great that it acts as a cosmic forge. In those final, incredible moments of heat and pressure, the simple atoms of hydrogen and helium are smashed together to form brand new, heavier elements. In the heart of the explosion, nuclear fusion happens at an incredible rate, creating carbon, oxygen, nitrogen, silicon, and iron, all the way up the periodic table. For the very first time, the universe was no longer just hydrogen and helium. It was being seeded with the building blocks of everything else. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was first created in the heart of a star that died billions of years ago. We are, literally, made of stardust. And these supernovae didn't just create these elements. They blasted them out across space at nearly the speed of light. They took the precious, newly forged metals and scattered them throughout the surrounding gas clouds, polluting the pristine cosmic soup. This was the most important recycling program in history. The universe was no longer pure and simple. It was now enriched, complex, and ready for the next act. This newly enriched gas, now containing all the ingredients for rocks, for planets, and for life, would now collapse to form the next generation of stars. But this time, because the gas contained these heavier elements that could help it cool and fragment more efficiently, the stars that formed could be a wider variety of sizes, including smaller, longer-lived stars like our sun. This changes everything. Before this pollution, the universe was a simple place. Now, it's chemically complex. This enriched gas is now like a soup that's had all the vegetables, herbs, and spices added to it. It's no longer just a bland broth. And this seasoned soup is now the raw material for the next generation of stars. But this time, the star-making process is different. Those new heavy elements, particularly dust grains made of carbon and silicon, are incredibly efficient at cooling down the gas clouds. Cooler gas can clump together more easily, and it can fragment into smaller, denser knots. This means that from this enriched gas, you don't just get behemoth stars. You can also form smaller, more stable stars, like our own sun, stars that can burn for billions of years, providing a stable energy source for any planets that might form around them. Now gravity, our patient architect, sees all this new, enriched, and now cooling gas and gets back to work. But its job description has just expanded. It's no longer just pulling together gas to form individual stars. It starts pulling together everything. Those first generations of stars, both the giants that went supernova and the smaller ones that lived longer, weren't born in isolation. They were born in clusters. Gravity begins to pull these star clusters together. It pulls together the massive clouds of now enriched gas. It pulls together the dark matter that we now know is also there, providing an invisible scaffolding. All of these things, star clusters, gas clouds, dark matter, begin to orbit a common center of gravity. And here's where physics does its beautiful dance. As this large, loosely organized swarm of stuff collapses inward, a wonderful thing happens. It begins to spin, and it naturally starts to flatten out. You can see this principle right in your own home. Think of a pizza chef tossing a spinning ball of dough into the air. As it spins, it flattens out into a disc. Or think of a figure skater pulling their arms in during a spin. They spin faster. This is conservation of angular momentum, a fundamental law of the universe. The same thing happened to our infant Milky Way. All the tiny random motions of the gas clouds and star clusters, as they were pulled together, averaged out into one general direction of spin. As everything collapsed inward, that spin accelerated and forced the material to form a vast rotating disk. The central region became a bulging sphere, the galactic bulge, while the outer material settled into the spinning disk we see today. This whole process didn't happen neatly or cleanly. Our galaxy wasn't built like a skyscraper from the ground up with a single blueprint. It was built through a process called hierarchical assembly, which is a fancy term for mergers and acquisitions. Imagine it as a cosmic game of Pac-Man. The early universe was full of small, dwarf, galaxy-sized clumps of stars and gas. Gravity pulled them toward each other. They merged, creating a larger structure. That larger structure then merged with other similar-sized structures. Over billions of years, through a series of these mergers, our majestic spiral galaxy was assembled piece by piece. It's a messy, violent, and slow process, but it's how all the big galaxies in the universe we see today were built. We can even see the fossilized evidence of this in our own galaxy. Streams of stars orbiting in the galactic halo, which are the torn-apart remains of smaller galaxies that were consumed by the growing Milky Way long, long ago. So, from the violent, creative deaths of the first stars, the stage was set not just for new stars, but for the grand architecture of galaxies themselves, our Milky Way being one magnificent example. So, let's picture our galaxy not as the elegant, stately spiral we often imagine, but as a toddler, a cosmic toddler, full of energy, chaos, and a habit of grabbing anything nearby and pulling it into its orbit. This young Milky Way was a far cry from the relatively orderly system we call home today. It was a wild place, a gravitational battlefield where the rules were simple. The biggest bully wins. And our galaxy was quickly becoming the biggest bully in our particular neighborhood. This process is what astronomers, with a delightful lack of PR concern, call galactic cannibalism. It's a stark term, but it's perfectly accurate. The Milky Way grew its immense size, not just by gently gathering loose gas, but by quite literally eating smaller galaxies that ventured too close. Gravity is an irresistible force, and if a tiny dwarf galaxy, containing perhaps only a few 100 million stars, found its path taking it near the burgeoning Milky Way, it was all over. The Milky Way's immense gravitational pull would seize it, stretching it, tearing it apart, and eventually digesting it, adding the smaller galaxy's stars, gas, and dark matter to its own growing body. And the most amazing part? This isn't just ancient history. It's happening right now. Our galaxy is still accreting, still consuming. We have several small satellite galaxies, like the large and small Magellanic Clouds, orbiting us right now. They are currently being pulled in, and billions of years from now, they too will be assimilated, becoming part of the Milky Way's extended halo. But we can also see the ghosts of mergers past. When a small galaxy is torn apart, it doesn't just vanish instantly. Its stars are stripped away in long, flowing streams that continue to orbit the Milky Way's center. These are like cosmic breadcrumbs, or more accurately, like the lingering swirls in a cup of coffee after you've stirred in the cream. They are tidal streams, and astronomers, with their powerful telescopes and sky surveying missions, can actually map these faint, ethereal rivers of stars. They are the fossilized evidence of ancient acts of cosmic consumption, the galactic equivalent of finding dinosaur bones in your backyard. One of the most dramatic of these ancient mergers has been nicknamed the Gaia sausage. Now, that might sound like something you'd order at a space-themed diner, but it's actually a fascinating discovery named for the European Space Agency's Gaia mission. The Gaia spacecraft is one of the most ambitious projects in astronomy. It's not just taking pictures of stars, it's meticulously mapping the precise positions, distances, and most importantly, motions of over 1 billion stars in our galaxy. It's like giving the Milky Way its first ever comprehensive census, and then making a movie of how everyone is moving. By analyzing this incredible trove of data, astronomers noticed something strange. A large group of stars in the inner halo of our galaxy weren't moving in random orbits. They were all moving in very radial, elongated orbits, like comets diving in toward the sun and then swinging back out. But the key was this: they were all doing it together, and their paths were all pointed in roughly the same directions. This was a telltale signature. It was the ghost of a dwarf galaxy that didn't just gently merge with us side on. About 10 billion years ago, this unfortunate galaxy, which scientists now call the Gaia Sausage Enceladus Galaxy, came screaming in for a head-on collision. It was a cosmic car crash of epic proportions.
This violent merger didn't just add stars to the Milky Way, it fundamentally reshaped it. The energy of the impact likely helped to puff up and thicken the nascent galactic disk, contributing to the thicker disk we see today. It was a pivotal moment in our galaxy's adolescence, a growth spurt triggered by a dramatic event, the evidence for which is still written in the paths of the stars it left behind. It's a history book written not in words, but in motion. Now, while all this chaotic merging was happening on the outside, something else was happening on the inside. All that gas and dust and all those stars being pulled together were, as we mentioned, starting to spin. And as they spun, they began to flatten out. This is a fundamental principle of physics. Think about that pizza chef again. They start with a ball of dough. As they spin it, the centrifugal force pushes the dough outward, and it naturally flattens into a wide, thin disk. The same thing happened to our galaxy. The random churning motions of the early cloud began to average out into one dominant direction of rotation. As everything collapsed inward, this spin accelerated, forcing the material into a frisbee-like shape. This is how the beautiful galactic disk we know today began to form. But at the very center of all this collapsing, spinning chaos, things were getting extremely intense. Imagine a crowded dance floor where everyone is moving toward the center. It gets incredibly packed. In the heart of the young Milky Way, an immense amount of mass, gas, dust, and stars
was piling up into a relatively tiny space. The gravity in this region became unimaginably strong. Scientists believe that it was here, in this ultra-dense environment, that a supermassive black hole was born. It likely started as a smaller black hole, perhaps from the death of a massive early star, and then grew insatiably by feeding on the plentiful gas and even entire stars that were unlucky enough to wander too close. It gorged itself, becoming the monstrous gravitational anchor we now call Sagittarius A. It's been sitting at the heart of our galaxy, a silent, dark king on its throne for almost the entire history of the Milky Way. Meanwhile, out in the newly forming disk, the conditions were becoming perfect for a new chapter. The gas here was now rich and complex, seasoned with all those heavy elements from countless supernovae. This enriched gas was far better at cooling down and clumping together than the pristine hydrogen and helium of the early universe. And so, a new, more diverse generation of stars began to ignite. These were stars like our sun, not too big, not too small, stable, and long-lasting. And because they formed from this chemically rich soup, something new and wonderful could happen around them: the formation of rocky planets. The heavy elements like iron, silicon, and oxygen could clump together to form dust grains, then rocks, then planetesimals, and finally, full-fledged planets. The stage was now set for worlds with solid surfaces, with minerals, with chemistry complex enough to potentially brew the ingredients for life. Our sun is a proud member of this later generation. It is a child of the Milky Way, born roughly 4.6 billion years ago from a cloud of gas that had been recycled through multiple generations of stars that lived and died long before it. Every single atom in your body that is not hydrogen or helium, the carbon in your cells, the nitrogen in your DNA, the oxygen in your lungs, the iron-carrying energy in your blood, was forged in the nuclear furnace of a star that died before our sun was born. That star ended its life in a spectacular supernova explosion, scattering these newly forged elements across space like a gardener scattering seeds. Those seeds eventually found their way into the cloud that would become our solar system, and, billions of years later, into us. We are not just living in the Milky Way. We are of the Milky Way. We are its consciousness, a way for the galaxy to know itself. The galaxy made us possible, and in a very real sense, we are its most intricate and wondrous creation. So, after billions of years of assembly, mergers, star formation, and stellar death, what does our completed, or rather, continually evolving galaxy look like today? All right, let's really try to wrap our minds around this. We need to build a model, a mental picture of our galactic home. But to do that, we first have to grapple with a scale that is frankly almost offensive to human intuition. Our brains evolved to understand the distance to a waterhole, the height of a tree, the scope of a valley. The scale of a galaxy is so far beyond that, it's almost a different kind of reality. So, let's start with the basic shape. The Milky Way is classified as a barred spiral galaxy. Now, if you've ever seen a picture of the Andromeda galaxy, which is our closest big galactic neighbor, you have a good idea. Imagine a giant pinwheel, but one where the very center isn't a perfect sphere of light. Instead, it has a bright, elongated bar cutting through it. From the ends of this bar, the majestic spiral arms unwind, curling out into space. That's us. That's what we'd look like from a bird's eye view. But the numbers involved are what truly stagger the mind. The diameter of this cosmic pinwheel, from one edge of its starry disk to the other, is about 100,000 to 120,000 light years. Now we throw that term around, light year, but we have to stop and really feel what it means. It's not a measure of time, it's a measure of distance. It's the distance that a beam of light, traveling at the fastest speed possible in our universe, can cover in a single year. And light is insanely fast. It zips around the Earth's equator about 7.5 times in just 1 second. In the time it takes you to snap your fingers, light could travel to the moon and back. Now hold that thought. Now imagine that incomprehensible speed kept up, not for a second, but for an entire year. The distance it would cover is 9.5 trillion kilometers. That's 9,500,000 kilometers. Or, if you prefer miles, about 6 trillion miles. That's 1 light year. Now multiply that by 100,000. That's the diameter of our galaxy. To travel from one side of the Milky Way to the other, even at the universal speed limit, would take you 100,000 years. Let's make that even more personal. The light from the stars you see at night, those tiny pinpricks of light, has been traveling for years, decades, even centuries to reach your eye. But the faint, misty band of the Milky Way itself is made of stars so distant that their light has been traveling for tens of thousands of years. The photons of light hitting your retina from, say, a star on the far side of the galaxy began their journey around the time when the first Homo sapiens were just beginning to leave Africa and populate the world. You are looking directly into the deep past, seeing those stars not as they are now, but as they were when humanity itself was in its infancy. That's the scale we're dealing with. It's a time machine as much as it is a telescope. Now, this galactic disk isn't a perfectly flat, two-dimensional pancake. It has some thickness to it, a bit of fluff. If the 100,000 light-year diameter is the width of a giant cosmic pizza, then the thickness is like the crust, about 1,000 light-years thick on average. This is the bustling, vibrant heart of the galaxy. This is where most of the action is. This is where you find the vast clouds of gas and dust, the nebulae, that are the nurseries for new stars. This is where you find the brilliant, young, hot blue stars that light up the spiral arms. It's the galactic equivalent of a busy downtown financial district, mixed with industrial zones and brand new housing developments, all buzzing with energy and construction. And where do we live in this vast metropolis? We are not downtown. We are not in the bright, chaotic core. We are out in the suburbs. Our solar system is located in one of the spiral arms, called the Orion Arm or the Local Spur, about 27,000 light years from the galactic center. This is a pretty good neighborhood. It's relatively quiet. We're far enough from the dense, crowded core to avoid its gravitational dramas and intense radiation. We have a nice, stable orbit around the galactic center, and this brings us to another breathtaking concept, the galactic year. Just as the Earth takes 1 year to orbit the Sun, our Sun, along with the entire solar system, is orbiting the center of the Milky Way. But this orbit is not a quick trip. The Sun is moving at a staggering speed of about 230 kilometers per second, or around 514,000 miles per hour around the galactic center. Even at that mind-melting speed, the journey is so vast that it takes us approximately 220 to 250 million Earth years to complete just one single orbit. This period of time is known as a cosmic year, or a galactic year. Let's sit with that for a second. The last time our solar system was in this exact same position in the Milky Way, the Earth looked very different. The continents were mashed together into the supercontinent Pangaea. The first dinosaurs were just beginning to appear and evolve into the giants that would later dominate the planet. The first mammals were tiny, shrew-like creatures hiding in the shadows. In the entire history of life on Earth, there have only been about 20 galactic years. Complex animal life has existed for perhaps only 3 of those orbits. The entire span of human civilization, from the first cities to today, is less than a blink of an eye, a tiny fraction of a single galactic second. This is the stately, slow, majestic pace of the galactic dance. We are whirling around the center at an incredible speed, yet the scale is so grand that we perceive none of it. Our entire species has existed for less than 1,000th of a single galactic orbit. It's the ultimate reminder that the universe operates on a timescale all its own, a rhythm of billions of years, and we are just fleeting visitors along for the ride. So, let's begin our tour. We're going to start from the very outer limits, the galactic equivalent of the remote, sparsely populated countryside that surrounds a bustling city, and we'll slowly make our way inward. This outermost region is called the galactic halo. Now, if you were to somehow float out here, it would be a very lonely and dark place. This isn't like the bright, sparkling disk of the galaxy we see in pictures. The halo is a vast, mostly empty, spherical cloud that envelops the entire galaxy. It's immense, stretching far beyond the visible edge of the starry disk, but it contains very little of what we traditionally think of as stuff. There's almost no gas and dust out here, and very few stars. If the Milky Way were a chandelier, the disk would be all the bright, glittering crystals, and the halo would be the faint, almost invisible web of wires and framework that holds it all together and gives it its shape. But just because it's mostly empty doesn't mean it's unimportant. In fact, the halo is home to the single biggest, most tantalizing mystery in all of modern science: dark matter. This is a concept that can boggle the mind, so let's take it slow. We've talked a lot about gravity, the force that holds the galaxy together. We can see the visible matter in the galaxy, the hundreds of billions of stars, the glowing gas clouds, the planets. We can add up all that mass and calculate how strong its gravitational pull should be. And then, we can watch how stars on the very outer edges of the galaxy's disk actually move. And here's where things get weird. They are moving way too fast. Imagine a merry-go-round. The horses on the outside have to move much faster than the ones near the center to complete a circle at the same time. That's basic physics. But now, imagine that merry-go-round is spinning so incredibly fast that the horses on the outside are whipping around with such speed that the centrifugal force should easily overcome the weak glue holding them on, and they should be flung off into space. But they aren't. They're staying on, perfectly fine. The only possible explanation is that there is a lot more glue than we can see. There must be some invisible, incredibly strong substance holding them on. That's exactly what's happening in our galaxy. The stars in the outer disk are orbiting the galactic center at velocities that should be impossible, based on the gravitational pull of all the visible matter we can detect. The math clearly says that at those speeds, these stars should have flown off into intergalactic space long ago. The fact that they haven't, the fact that our entire galaxy hasn't simply flown apart, means there must be a huge amount of additional mass that we cannot see. Its gravity is providing the extra glue needed to hold everything together. This invisible mass is what we call dark matter. We call it dark because it doesn't interact with light at all. It doesn't emit it, absorb it, reflect it, or bend it. Well, it does bend it through gravity, but that's a different story. It is completely and utterly transparent. Our telescopes, which are essentially fancy light collectors, are blind to it. We only know it's there because of its gravitational muscle. And it's not just a little bit of it. Based on the motions of stars, we've calculated that this dark matter halo is colossal, containing about 10 times more mass than all the visible stars, gas, and dust in the Milky Way put together. Think about that. Everything you can see in a picture of a galaxy, every single star, every nebula, is just the glittering decoration on top of an immense, invisible mountain of dark matter. This dark matter halo is the true skeleton of our galaxy. It's the framework that formed first after the Big Bang, and the normal visible matter then fell into its gravitational wells to form the stars and galaxies we see. Without dark matter, the Milky Way as we know it would never have formed. It is the ultimate cosmic phantom, and figuring out what it actually is, what tiny, exotic particle could make up this vast, invisible ocean of matter, is one of the greatest scientific quests of our time. But the halo isn't just empty space and mysterious dark matter. It's also a cosmic museum, home to the most ancient relics in the galaxy. Floating out here in the darkness are the oldest stars we know of, over 13 billion years old. These are the survivors from the Milky Way's very infancy, formed from the pristine hydrogen and helium gas that existed before many stars had died and enriched the cosmos. Many of these ancient stars are found in spectacular structures called globular clusters. Imagine a beehive, but instead of bees, it's a dense, spherical swarm of hundreds of thousands of stars, all gravitationally bound together in a ball that might be only 100 light years across. The density of stars in the core of one of these clusters is incredible. If you lived on a planet there, your night sky would be ablaze with thousands of stars as bright as our Venus, creating a perpetual, dazzling twilight. There are about 150 of these globular clusters orbiting our galaxy, like a cloud of distant fireflies, each one a stunning dense island of ancient light. The stars in these clusters are known as population 2 stars. Astronomers classify stars into populations based on their metal content. Now, remember, to an astronomer, a metal is any element heavier than helium. So, population 2 stars are metal poor. They have very low concentrations of elements like carbon, oxygen, and iron. This is because they were born from gas that had been polluted by only the first few generations of supernovae. Their chemical composition is a time capsule, telling us what the universe was like before it was seasoned with the heavier elements. Studying them is like reading a history book from the first chapter of the galaxy. When you look at a globular cluster through a telescope, you are not just looking across space. You are looking back in time, seeing stars that have been shining since before the Milky Way's disk had even fully formed. Besides these clustered ancient stars, the halo is also strewn with isolated old stars and, perhaps most poetically, the ghostly remains of galaxies past. As we learned, the Milky Way grew by consuming smaller dwarf galaxies. When that happens, the victim galaxy is torn apart by our galaxy's gravity, but it doesn't just disappear. Its stars are pulled out into long, looping streams that continue to orbit the galactic center. These are called stellar streams or tidal streams. They are the cosmic equivalent of a faint, ethereal smoke ring, the lingering evidence of a dramatic galactic meal that happened billions of years ago. Astronomers are now mapping dozens of these faint rivers of stars in the halo, each one telling the story of a smaller galaxy that was absorbed into our own, its stars now joining the vast, silent dance in the darkness. So, the halo, though seemingly empty, is actually a place teeming with history, mystery, and the ghosts of galaxies long gone. Moving inward from the halo, we enter the main body of the galaxy, the galactic disk. This is the most iconic part of the Milky Way, the part we see as that river of light in the night sky. The disk is where the galaxy is alive with activity. It's a complex structure, actually composed of a thin disk and a thick disk. The thin disk is where you find the youngest stars, including our Sun, and the vast majority of the galaxy's gas and dust. This is the site of ongoing star formation. The thick disk contains somewhat older stars that orbit a little higher above and below the galactic plane. The disk is not a featureless plane. Its most prominent features are the majestic spiral arms. From our vantage point inside the disk, it's very difficult to map our own galaxy's spiral structure. It's like trying to map the shape of a forest while standing in the middle of it. But through careful observations of the positions and distances of stars and gas clouds, astronomers have pieced together a picture.
The Milky Way is a barred spiral, meaning its center is not a sphere but an elongated bar of stars. From the ends of this bar, the spiral arms unwind. We believe there are four major arms: the Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, and the Norma arm. Our solar system is located in a smaller, partial arm called the Orion Cygnus arm, or simply the local arm, which branches off from the larger Sagittarius arm. You might wonder, are these arms like solid structures, like the fins of a pinwheel? Actually, no. The spiral arms are not permanent structures made of the same stars. They are waves of density, like traffic jams on a cosmic freeway. Imagine a highway where cars are moving along, but there's a construction zone that causes a slowdown. Cars enter the slowdown, they bunch up and move through it more slowly, and then they exit and speed up again. The slowdown itself, the traffic jam, moves along the highway much more slowly than the individual cars. The spiral arms are like that. They are waves of compressed gas and gravity that move through the galactic disk. As clouds of gas and dust enter a spiral arm, the increased density triggers gravitational collapse, leading to a burst of new star formation. This is why the spiral arms appear so bright and prominent. They are lined with brilliant, short-lived, massive blue stars and the glowing pink clouds of gas, nebulae, that are stellar nurseries. These massive stars live for only a few million years and die as supernovae before they can leave the arm. So, the arm is always full of them, making it stand out. Older, longer-lived stars, like our Sun, simply pass through the arms on their orbits, spending most of their time in the less dense regions between arms. And it's within these spiral arms, in the vast clouds of gas and dust in the thin disk, that the magic of star birth happens. These clouds are called nebulae, singular nebula, and they are among the most beautiful objects in the universe. A typical nebula is composed of about 70% hydrogen, 28% helium, and that crucial 2% of heavier elements, the dust, which is mostly carbon and silicon compounds. These nebulae are cold, only about 10 to 20 degrees above absolute zero, and they are enormous, often light years across, and containing enough material to form thousands of stars. The process begins when something disturbs the nebula, perhaps the shock wave from a nearby supernova explosion, or the gravitational tug of a passing star, or simply the natural ripples of the density wave in a spiral arm. This disturbance causes a region of the cloud to begin collapsing under its own gravity. As it collapses, it fragments into smaller and smaller clumps. Each clump, a protostar, continues to fall inward,
heating up dramatically at its core. When the core temperature hits about 10 million degrees Celsius, a miracle occurs. Nuclear fusion ignites. Hydrogen atoms are fused together to form helium, releasing a tremendous amount of energy in the process. A star is born. The newborn star blows away the remaining gas and dust around it, often revealing itself in a beautiful stellar nursery like the Orion Nebula, which is visible to the naked eye as a fuzzy star in Orion's sword.
But the story doesn't end with the star. The leftover dust and gas that didn't get incorporated into the star often forms a swirling disk around it, called a protoplanetary disk. Within this disk, dust grains collide and stick together, eventually growing into pebbles, then rocks, then planetesimals, and finally, planets. This is how our own solar system formed 4.6 billion years ago. Every star you see in the night sky likely has, or had, planets orbiting it. The galaxy is teeming with worlds. We have now discovered over 5,000 of these exoplanets, and the number grows all the time. They come in a bewildering variety. Hot Jupiters orbiting scorchingly close to their stars, super-Earths, rocky planets larger than our own, ice giants, and even potential Earth-like worlds orbiting in their star's habitable zone, where temperatures might be right for liquid water to exist. The sheer number of stars in the Milky Way, estimated between 100 and 400 billion, suggests an almost unimaginable number of planets. The potential for life out there is a question that drives modern science. Stars live out their lives based on their mass. The most massive stars, as we mentioned, are brilliant, blue, and short-lived. A star 10 times the mass of the Sun might only shine for 20 million years. A star like our Sun, a yellow dwarf, has a much more sedate life, steadily burning its hydrogen for about 10 billion years. And the smallest stars, red dwarfs, are so frugal with their fuel that they can shine for trillions of years, longer than the current age of the universe. But for all stars, the fuel eventually runs out. The death of a star is as important as its birth, for it is in death that stars give back to the galaxy, enriching the interstellar medium with the heavy elements forged in their cores. For a star like the Sun, the end is relatively peaceful. In about 5 billion years, it will exhaust the hydrogen in its core. It will swell into a red giant, swallowing the inner planets, probably including Earth, before gently puffing its outer layers out into space, creating a beautiful glowing shell of gas called a planetary nebula. The hot core left behind will become a white dwarf, a Earth-sized ember that will slowly cool over billions of years. But for stars more than about 8 times the mass of the Sun, death is spectacularly violent. They end their lives in a cataclysmic explosion known as a supernova. For a brief moment, a single supernova can outshine its entire host galaxy. In the incredible inferno of the explosion, elements are forged through rapid nuclear fusion and neutron capture, creating all the elements heavier than iron on the periodic table, like gold, silver, platinum, and uranium. The explosion blasts these newly created elements, and the stars remains out into space at tremendous speeds, creating an expanding shock wave that can travel for hundreds of light years. This shock wave, in turn, can compress nearby gas clouds, triggering the next round of star formation. It's a magnificent cycle of life, death, and rebirth on a galactic scale. The debris from the supernova, rich in heavy elements, mixes with the interstellar medium, ensuring that the next generation of stars and planets will be made from this enriched material. The very iron in your blood, the calcium in your bones, and the oxygen you breathe were all created the remnant of a supernova is something even more exotic than a cloud of expanding gas. If the core of the exploded star was particularly massive, it can collapse into an unimaginably dense object, a neutron star or a black hole. A neutron star is the city-sized core of a dead star, cramming more than the mass of our sun into a sphere only about 20 kilometers across.
A single sugar cube-sized piece of neutron star material would weigh as much as a mountain. They spin incredibly fast, often dozens of times per second, and if they have a strong magnetic field, they can beam out radiation like a cosmic lighthouse. When these beams sweep across Earth, we detect them as precise pulses of radio waves, and we call these objects pulsars. They are nature's most accurate clocks. Black holes are even more extreme. They are regions of space where gravity is so intense that nothing, not even light, can escape from them. The boundary around them from which nothing can return is called the event horizon. Stellar mass black holes formed from the collapse of massive stars typically weigh between about 5 and 50 solar masses. They are scattered throughout the galaxy. We can't see them directly, but we can detect them by their gravitational influence on companion stars or by the X-rays emitted by the hot gas swirling into them from a nearby star. Now, let's journey to the very heart of the galaxy, the galactic bulge and center. This is the bustling downtown of the Milky Way, a region about 10,000 light-years across, packed tightly with stars. If you were standing on a planet near the galactic center, your night sky would not be dark. It would be ablaze with the light of millions of stars, many times brighter than a full moon on Earth. The stars here are mostly old, population 2 stars, and they orbit the center in every possible direction, creating a swollen, football-shaped central bulge. But the true ruler of this domain lies hidden at the very exact center, a monster lurking in the light, Sagittarius A star. This is the supermassive black hole at the heart of our galaxy. For decades, astronomers suspected its existence based on the frantic orbits of stars near the center, which were whipping around an invisible, incredibly massive object. Then, in 2022, the Event Horizon Telescope collaboration, a global network of radio telescopes, did the impossible. They took a picture of it. Well, not of the black hole itself, but of its shadow, the dark silhouette against the glowing, superheated gas swirling around its event horizon. Sagittarius A star is immense. It contains about 4.1 million times the mass of our Sun. Yet despite its size, it's currently a relatively quiet and gentle giant. It's not consuming large amounts of material, so it's not shining brightly as an active galactic nucleus or quasar. Some material does fall in, creating a flickering glow, but it's mostly dormant. However, its gravity is the master conductor of the galactic core. The stars that orbit closest to it move at breathtaking speeds. One star, known as S2, comes within just 11 billion miles of the event horizon. That's only about 3 times the distance from the Sun to Neptune. And at its closest approach, it accelerates to a staggering 15 million miles per hour, which is nearly 3% the speed of light. Studying the orbits of these stars is what allowed astronomers to precisely measure the black hole's mass. This region is a natural laboratory for testing Einstein's theory of general relativity under the most extreme gravitational conditions imaginable. Our galaxy is not alone. It is part of a small gang of galaxies gravitationally bound to each other, known as the local group. The local group is about 10 million light-years across and contains more than 50 galaxies. The 2 biggest members are our Milky Way and the Andromeda Galaxy, M31, which is slightly larger than us. The third largest is the Triangulum Galaxy, M33. The rest are mostly smaller dwarf galaxies that orbit the two big spirals like satellites. The most famous of these are the Large and Small Magellanic Clouds, two irregular dwarf galaxies easily visible from the southern hemisphere. They are currently orbiting the Milky Way and will likely be absorbed by our galaxy billions of years from now. But the most dramatic future event for our galaxy is on a collision course with us. The Andromeda Galaxy is hurtling towards the Milky Way at about 110 kilometers per second. In about 4.5 billion years, the two galaxies will begin a slow gravitational dance that will eventually merge them into a single, giant elliptical galaxy, often nicknamed Milkomeda. It's important to know that a galactic collision is not like two cars crashing. Galaxies are mostly empty space. The stars are so far apart that it is extremely unlikely any two stars will actually collide. Instead, the galaxies will pass through each other, their gravitational fields dramatically distorting each other's shapes, triggering immense waves of new star formation before settling down into a new blended structure. Our solar system will likely be flung out into a new orbit, but it will probably survive the encounter unscathed. The night sky from Earth, if it still exists then, would be transformed beyond recognition. So after this grand tour of our magnificent, bustling galactic home, it's only natural to wonder, what happens next? What is the ultimate destiny of the Milky Way? It's a story written on a time scale so vast it defies human imagination. A slow-motion ballet that will play out over epochs longer than all of human history to date. It's a future that is, perhaps surprisingly, not one of fire and fury, but of a long, slow, and quiet fading. The dramatic, chaotic youth of our galaxy is largely behind it. The era of major mergers, of galactic cannibalism, will eventually come to an end. Our impending collision with the Andromeda Galaxy, about 4.5 billion years from now, will be one of the last great acts of violence in our local cosmic neighborhood. After that merger, which will create the new giant galaxy some are calling Milkdromeda or Milkomeda, the universe itself will be working against any further growth. The expansion of the universe, which is actually accelerating due to that other great mystery, dark energy, will eventually push all other galaxies so far away from our own local group that they will fade from view, receding over a cosmological horizon. Our newly merged galaxy will find itself alone in an ever-darkening void, an island universe in the true sense of the word. But inside our galaxy, life, in a stellar sense, will continue for a long, long time. However, it's a life that is slowly winding down. The primary driver of this decline is fuel. A galaxy is like a vast engine, and its fuel is the cold, neutral gas that floats between the stars, mostly hydrogen. This is the raw material for new stars, but this gas is a finite resource. It gets used up. Some of it gets locked away forever in stars, especially long-lived ones. Some of it gets blown out of the galaxy entirely by powerful supernova explosions. And as the galaxy ages, less and less new gas is accreted from intergalactic space. The rate of star formation, therefore, is not constant. It's like a campfire that's slowly burning through its pile of wood. It peaks early, and then begins a long, slow decline. In about 1 trillion years from now, the last of this usable gas will be exhausted. The last star will be born. It will likely be a small, faint red dwarf, sputtering to life in some forgotten corner of the galaxy. And after that, silence. No new stars will ever form again. The galactic engine will have run out of fuel. From this point on, the story of the Milky Way becomes a story of subtraction, of things ending, of lights going out. The first to go, relatively speaking, are the brilliant, massive stars, but they are already gone. Stars much more massive than our sun live for only a few million years. They are the mayflies of the cosmos, shining with a fierce blue-white intensity, but dying young in spectacular supernova explosions. They will have vanished from the scene eons before the final star is born. Next are the stars like our own sun. Our sun has a total lifespan of about 10 billion years. It's middle-aged now. In about 5 billion years, it will exhaust the hydrogen fuel in its core, swell into a red giant, likely engulfing the inner planets, and then gently puff its outer layers away into a beautiful planetary nebula, leaving behind its incredibly dense, Earth-sized core, a white dwarf. This white dwarf will initially be searingly hot, a ember of what once was, but with no internal fusion to keep it warm. It will slowly, inexorably cool down over billions of years. Every star like our sun will follow this path. They will die not with a bang, but with a whisper, leaving behind these fading white dwarf remnants. So, who is left in this trillion-year-old future? The galaxy's population will be dominated by two groups. The first is the long-lived red dwarfs. These are the smallest and coolest kind of star. They are incredibly frugal with their nuclear fuel, burning it so slowly that their lifespans are measured in trillions of years. A red dwarf born near the beginning of the galaxy is still in its infancy today. In the far future, these dim, red stars will be the sole sources of light and warmth in the galaxy. They will be the last living stars. The second group is the dead. The galaxy will be filled with the cooling embers of past stellar generations. The white dwarfs, the cores of sun-like stars, the neutron stars, the ultra-dense cores left from supernovae, and black holes, both stellar mass and the supermassive one at the center. This will be the galaxy's population, a handful of faint red living stars amidst a vast sea of dark, dead stellar corpses. The character of the galaxy will change completely. It will grow darker and redder. The brilliant blue-white light of young star clusters and the glowing pink of stellar nurseries will be gone forever. The only light will be the faint, ruddy glow of the countless red dwarfs. It will be a somber, quiet place. But even the red dwarfs are not immortal. Their incredible longevity is still finite, on timescales so long that they have no meaning to our human experience. Tens of trillions, even hundreds of trillions of years, the last red dwarf will finally, reluctantly, use up the last of its hydrogen fuel. It will not go out with a dramatic explosion. It will simply fade, cooling into a dark, inert ball of gas known as a black dwarf. It will join the other remnants. In about 1 trillion years from now, the last of this usable gas will be exhausted. The last star will be born. It will likely be a small, faint red dwarf, sputtering to life in some forgotten corner of the galaxy. And after that, silence. No new stars will ever form again. The galactic engine will have run out of fuel. From this point on, the story of the Milky Way becomes a story of subtraction, of things ending, of lights going out. The first to go, relatively speaking, are the brilliant, massive stars, but they are already gone. Stars much more massive than our sun live for only a few million years. They are the mayflies of the cosmos, shining with a fierce blue-white intensity, but dying young in spectacular supernova explosions. They will have vanished from the scene eons before the final star is born. Next are the stars like our own sun. Our sun has a total lifespan of about 10 billion years. It's middle-aged now. In about 5 billion years, it will exhaust the hydrogen fuel in its core, swell into a red giant, likely engulfing the inner planets, and then gently puff its outer layers away into a beautiful planetary nebula, leaving behind its incredibly dense, Earth-sized core, a white dwarf. This white dwarf will initially be searingly hot, an ember of what once was, but with no internal fusion to keep it warm, it will slowly, inexorably cool down over billions of years. Every star like our sun will follow this path. They will die not with a bang, but with a whisper, leaving behind these fading white dwarf remnants. So, who is left in this trillion-year-old future? The galaxy's population will be dominated by two groups. The first is the long-lived red dwarfs. These are the smallest and coolest kind of star. They are incredibly frugal with their nuclear fuel, burning it so slowly that their lifespans are measured in trillions of years. A red dwarf born near the beginning of the galaxy is still in its infancy today. In the far future, these dim red stars will be the sole sources of light and warmth in the galaxy. They will be the last living stars. The second group is the dead. The galaxy will be filled with the cooling embers of past stellar generations. The white dwarfs, the cores of sun-like stars, the neutron stars, the ultra-dense cores left from supernovae, and black holes, both stellar mass and the supermassive one at the center. This will be the galaxy's population, a handful of faint, red, living stars amidst a vast sea of dark, dead stellar corpses. The character of the galaxy will change completely. It will grow darker and redder. The brilliant blue-white light of young star clusters and the glowing pink of stellar nurseries will be gone forever. The only light will be the faint, ruddy glow of the countless red dwarfs. It will be a somber, quiet place. But even the red dwarfs are not immortal. Their incredible longevity is still finite, on timescales so long that they have no meaning to our human experience. Tens of trillions, even hundreds of trillions of years. The last red dwarf will finally, reluctantly, use up the last of its hydrogen fuel. It will not go out with a dramatic explosion. It will simply fade, cooling into a dark, inert ball of gas known as a black dwarf. It will join the other remnants.
And what of the white dwarfs? They will have continued to cool during all this time. A white dwarf starts white hot, but over many billions of years, it will cool to yellow, then red, and eventually it will emit no visible light at all. It will become a black dwarf, a cold, dark sphere of crystallized carbon and oxygen, perhaps resembling a giant, planet-sized diamond, drifting in the absolute zero cold of space. The process of a white dwarf cooling to a black dwarf takes so long that it's believed the current age of the universe, 13.8 billion years, is not even long enough for the first white dwarfs to have reached this state. The first black dwarf in the universe has not yet been born. So, the galaxy's final state will be a dark graveyard, a vast collection of black dwarfs, neutron stars, and black holes, all silently, eternally orbiting the galactic center. There will be no light, no heat, no new energy. It will be a frozen, mechanical clockwork of orbits in the profound dark. And what of the great anchor at the center? The supermassive black hole Sagittarius A. Even its reign is not forever. Thanks to a strange quantum mechanical process predicted by Stephen Hawking, black holes are not entirely black. They can slowly lose mass by emitting a faint trickle of particles now known as Hawking radiation. For a massive black hole, this process is incredibly slow. A black hole with the mass of our sun would take longer than the current age of the universe to evaporate. For a supermassive black hole millions of times heavier, the time scale is almost unimaginably long.
on the order of 10 years, a 1 followed by 100 zeros, a number so large it has its own name, a Google. But given enough time, even this monstrous beast will, in a final burst of energy, evaporate completely away. This is the far, far future as we currently understand it, a quiet, dark, and cold end. But it's important to remember that this is not an ending in the sense of a tragedy. It's a natural conclusion to the life cycle of a galaxy. The Milky Way had a vibrant, brilliant, and creative life. It forged the elements and built the worlds that allowed for us to exist and to look up at the night sky and wonder. Its story, from a tiny ripple in the early universe to a glittering spiral to a dark relic, is one of the most epic narratives it is possible to conceive. And in a way, the fact that we can understand and tell this story is a beautiful and profound counterpoint to that distant darkness. We are the universe's consciousness, and for a brief shining moment, we are here to bear witness to its majesty. But for now, for us, the Milky Way is a vibrant, dynamic, and beautiful home. It is a cosmic engine that has taken the primordial hydrogen from the Big Bang and processed it through generations of stars, creating the diversity of elements that allowed for planets, oceans, and life. Every time you look up at that faint milky band in the night sky, remember what you are truly seeing. You are seeing the collective light of countless suns. You are seeing the stellar nurseries where new solar systems are being built. You are seeing the radiance of stars that died long ago, whose remains now reside in you. You are looking at the vast spiral disk in which we have our being, the invisible halo of dark matter that holds it all together, and the distant, mysterious center, where a silent giant holds sway. It is our city of stars, and we are, for a fleeting moment, conscious citizens within it. We are part of this grand story, a story that began over 13 billion years ago, and will continue for trillions more. And that connection, that sense of belonging to something so vast and beautiful, is perhaps the greatest gift that exploring our Milky Way galaxy